Hello Internet, my name is Quinn and this is Blondihacks. I'm working on the Pennsylvania A3 switcher locomotive this week, and it's a big day because we're going to make first chips on the locomotive proper. I mean, not counting the couple hundred hours or so we spent on the boiler, if you count that, but today we're going to make the frames. And these are really obviously the defining structure of the locomotive, and these need to be accurate because everything we build on the locomotive is going to reference and sit on these frames. So we got to make it good. Let's go right now. The first and most important decision on the locomotive frames is material choice. I've chosen to go with brass for this, but steel would also be an option. I've got these two great big brass bars for the purpose, and I'm actually able to get both frames out of either one of these bars, so my first job is to figure out which one is the straightest one. The first most important thing for any frame rails on any kind of vehicle is that they have to be straight and square, as straight as you can possibly get them, and the next most important thing is that the frames have to be identical one to the other. So you'll see how we solve that latter problem in a minute. But lucky for me, one of these bars is very, very straight, so I won't have to straighten anything first before I use it. So why did I go with brass? Well, this is a good excuse to talk a little bit about factor of adhesion in locomotives. Steel wheels on steel rails is great for efficiency. You get extremely low rolling resistance, which means you don't need a lot of power to pull extremely large loads. It's one of the reasons that toy locomotives can pull around full-sized humans. Some of us are a little more than full-sized these days, but it's a Faustian bargain. The price we pay for that low rolling resistance is extremely poor static friction, which means one of the most difficult things for a locomotive is to start rolling and to stop rolling, because we have very, very little traction. So maximizing traction is extremely important. The main way you do that in a locomotive is weight. Steam locomotives are rated in tractive effort, which is kind of an old-timey analog to horsepower. It's a back-of-the-napkin kind of number that's derived from piston diameter, stroke, boiler pressure, and driver diameter. However, making power is the easy part. Getting traction is the hard part. So locomotives are also rated by factor of adhesion, which is weight on drivers divided by tractive effort. So tractive effort generally very high, so we need weight on drivers to be very, very high to keep our factor of adhesion from getting too low. The real machines aim for roughly 4.0 factor of adhesion. However, physics doesn't scale down linearly. We scale our models down linearly, but most of the physics are either cube relationships or square relationships with size. So when we scale down these models, what we actually end up with is something that is vastly, vastly overpowered and has very little traction. A factor of adhesion of 2.0 is very, very good for a model. If you can get that, you're doing well. Most of them are somewhere in the 1 to 1.5 range, which means they have a lot of trouble getting rolling when they're pulling a load. So the moral of all that is anything we can do to improve weight over drivers is a very, very good thing. And that was a primary reason I chose brass for these frames, because brass is quite a bit heavier than steel. Brass is also a joy to machine. It's a real pleasure to work with. And not for nothing, this material was free. It was donated to the channel by a viewer for the purpose of making these frames, and that was also a substantial factor in my decision. If you're worried about strength, don't be. Both brass and steel are plenty strong enough for locomotive frames of this size. If you were building a much larger locomotive, if you were building this thing in 1/8 scale, something like that, then yeah, you might want to start thinking about steel for strength reasons, but on a 3.5 inch gauge locomotive, brass is just fine. Now you've been watching me rough cut these bars a little bit oversized, and now I'm going to start squaring them up. I'm using some adjustable parallels on the ends of my fixture plate for extra support since the bars are so long, and I'm going to create a reference face all the way down one side and square up one end. One of the interesting challenges I have with these frames is that my mill actually doesn't have quite enough table travel to get the cutter all the way down the long sides. Even if I position the piece on the table at the extreme end of cutter reach at one end, I come up about 1/4 inch short at the other end. But that's okay because actually most of that gets cut off at the end, so we can kind of work around that. But for now, we'll just leave that one end unfinished. After finishing one long side and one short side, I now have a reference corner that I've marked, and that corner will be used for all measurement and layout on this frame. Now I can flip it around, and I'm using a parallel and pins on my fixture table to keep things aligned to the mill table. Those fixturing pins are aligned with the x-axis of the mill, so I can put that reference edge that we just created now up against that parallel, which is up against those pins, tappy tap tap it nice and snug, and I can mill the other side, and I know it's going to end up parallel to our reference side. These are really long cuts, but it's important in the machine shop to always maintain your focus and a serious sense of purpose, because these machines are dangerous and you don't want to lose concentration, so keep your mind on your work and pay attention even on these long, boring cuts. At this point, the bars are both finished almost all the way around except for that one end, but they're still oversized. I'm just checking how the cuts are going. They're both very, very close to each other, so that's good, but they do have about 2 thou of taper, which, over 17 inches, that's actually not too bad. Here you can see how I couldn't quite get to the ends of those cuts, but that's okay. We'll be cutting off all that material at the end anyway. These bars are still over length, and there's an angled horn feature at the end that's going to remove all of that unshapen material. You can see I've marked my reference corners as well on both frames. Now, here's how we're going to solve the problem of making the frames identical, and you knew this was coming. We're going to screw them together, and we're going to do all of the machining as though they were one part. I'm going to start by lining up my reference corners, and I'm going to lay out some fixturing screws. We're going to screw them together, and these screws are all positioned in areas that will be removed in the final frames, so none of these screws will create any rogue speed holes in the final parts. I'm lining up the reference edges as best I can, and then clamping them together, but this doesn't actually have to be perfect because I'm going to machine all 4 sides of the frames again after they're bolted together. To guarantee that they're as perfectly identical to each other as I can get them, I've left them oversized so that I can do final dimensioning after they're screwed together. I just needed them to be very, very close to final dimension and have machined edges so that I could align them properly before screwing them together. Now I can drill and tap the screw holes and bolt them together, and then we can finish. I drill tapping size all the way through both bars, then I drill clearance size just through the top bar. Then I can come in with the tap and I can run the tap down through the clearance hole and tap the lower bar. Then I'll be able to clamp these pieces together with a clearance hole on one and a threaded hole in the other, and they will be perfectly aligned. And once again, Kozo very helpfully and cleverly tells you exactly where to put these fixturing screws so that they will all end up in areas that are either removed or where you actually need a hole anyway in the final frames, so you'll never know these screws were ever here. Also importantly, I'm countersinking these screw holes with my shop-made countersinking D-bit. This is so that the screws sit flush. I actually need them to be a little below the surface. I want to make sure of that to guarantee that the screw heads don't interfere with any subsequent setups. And we need it to be like these screws were not even here. And that looks really good. I can sweep my scale right over that, no contact with that screw head at all. Very nice. These bars are now as one, and we will be leaving them this way for a very long time. So, buckle up. You could also, I suppose, try soldering these bars together. You might be able to super glue them together. If they were steel, you could tack weld them together. Although you got to make sure that your tack welds don't interfere with any of your setups. There's various ways to do this. Now, however, that they're bolted together, I can remachine the outside and bring them down to final dimension. You'll note that I've got Sharpie mark on the parallel sides, because when you're remachining an already machined surface, it can actually be difficult to tell if you're fully cleaning up both cuts. So Sharpie mark ensures that your cut is deep enough that you're fully recutting the surfaces. Okay, it's layout time, and we've got to use the good stuff. No Sharpie mark for this because we're going to be doing a bunch of layout lines, and all of it needs to survive through many operations and setups. Sharpie is awesome for quick and dirty layout because it's really fast, it dries really fast, you don't have to prep the surface, but it doesn't survive very long. Sharpie is very fragile, unless it's somewhere where you don't want it, in which case it's somehow maddeningly permanent. For this layout though, it's time for the good stuff. It's time for the die-chem. And in fact, I have a shiny, brand new bottle of it. And this is the best. Brand new die-chem is so nice. It works so much better. This stuff really doesn't work very well when it gets too old. It doesn't cover well. It doesn't dry very well. It dries too thick. It chips and flakes when you try to scribe it. It's terrible. But the brand new stuff is delightful. I'm going to be doing the actual machining of all these features to the DRO. However, I really like having layout lines on a complex part like this because it's a great sanity check to make sure I'm kind of in the right place for each cut. And it helps me maintain the orientation of the part relative to the drawing in my head because It's very easy to flip apart in your head or transpose it or forget which side you're supposed to be working on, that kind of thing. Layout really helps with keeping things straight. It also makes you feel like a pleasant Australian clockmaker. All right, let's make some chips on these frame features. I'm going to start with this big rectangular area that needs to be removed. I'm going to chain drill some holes, which is going to give me clearance for a hacksaw blade. This is Kozo's suggestion for how to do this in the book. This would be a lot of material to just turn into chips. You could certainly do that, but we can also easily save the materials, so we might as well do that. So I got all set up to do that, got my hacksaw clearance. Then I remembered hacksaws are for chumps, and I have a bandsaw. That drilling wasn't a total waste of time though, actually. I was able to use it to sneak the bandsaw blade in and get it lined up straight with the bottom edge of this cut, which actually allowed me to save quite a bit of this material in the center. It saved me having to turn all that material into little triangles to get the bandsaw lined up with the final edges. However, wouldn't you know, my little bandsaw didn't quite have enough throat depth to finish the long cut. So in a bit of instant karma for my bad-mouthing of the lowly hacksaw, which has served metalworkers extremely well for 100 years, I got to finish this cut with the character builder saw. Now, one thing to know about brass is that it is extruded material. And extrusion is very much like cold rolling in steel, in that the process puts a lot of internal stresses into the material. And when you do that, when you cut a large chunk out of that material, like more than halfway through, like we've done here, the material tends to warp. I put the frame on my surface plate to check for that, and indeed I do have a little bit of banana. You can see I've got a slight rock in there now, where that thin spine of material has bananaed away from the cut. That's typically what happens. So it's just a little bit, it's almost not worth fixing, but I decided, got the apron on, I'm all dressed up, I might as well fix it. I set it up on the little arbor press, and I gave it just a little love squeeze. It doesn't need much, just a little bit to bend it back the other way. One little bit of lean is all I gave it. You don't want to go too far, of course. And that's all it needed. Put it back on the surface plate, and that little bit of rock that it had is now completely gone. Double checking the other side with a light, and I don't see any bowing, any light showing through underneath there anywhere. So I think we're good. The second large cut is for the front axle box, and that also bananaed a little bit, so I did the same thing there. Also a straightforward fix. Now we can go back over to the mill and finish machining those rough cuts. Got my hammer edge finder in there, and I'm finding my reference corner, which you might recall that I still have marked on both of these frames, and that's a very important reference. I'm going to do all of my milling now. There's really no more risk of bananaing this material. We've cut out the big chunks, so we can do all the finish machining, and there's a bunch of smaller features that we're going to cut, but nothing's really at risk of bananaing anymore. On that subject of material choice again, I was actually originally planning to use steel, and I was going to use hot-rolled plate, not the cold-rolled, which is usually preferred by machinists. The reason for hot-rolled in this application is that hot-rolled material has not been pushed through dies and does not have those internal stresses in it that cold-rolled and extruded materials do. So it does not banana when you machine it. You have to deal with the mill scale, of course, but you can either grind that off or dissolve it in acid. There's various ways to get rid of that. However, as I said, this brass material fell in my lap, which kind of hurt because it's heavy, but I decided to use it. This cut, though, I have to say, was not going great. It was making a lot of noise, and it didn't feel like it was cutting very well. And the surface finish is, frankly, poop. I plowed my way through anyway in the endurance racing spirit of, if the car's not on fire, stay out. But when I was done, I took a close look at that end mill, and sure enough, one of those teeth is kind of folded over if you look at it real close under magnification. The other one is just fine, but one of them is dinged over. It looks like it's probably been dropped. I don't remember dropping this end mill, but it looks like it's been dropped, and well, frankly, I don't remember a lot of things. However, this is a second-hand end mill, so I'm going to go ahead and blame the previous owner. What I do with tools like this is mark the bad end with orange nail polish, which is extremely durable and will survive many years, because the side flutes on this mill are still perfectly fine. I can do lots more side milling on it. I just want to remind myself not to use this one end of it. Someday I could try regrinding it, but I don't need to right now. I frankly have a lot of half-inch end mills, so I'm not worried about it. Flipping the frames over now and finding my reference corner once again, we've got a bunch of features to do on this side of the frames. First up is that front axle box, which you can see I've already roughed in. Now the drawing specifically calls for a 1/32 radius on the inside corners of that, and it's called out specifically in the build notes as well as being important. Now you could buy some sort of exotic 1/32 ball nose end mill for that, or you could do what I did and just go through all your end mills and look for one that has a corner radius of 1/32 on it. That's actually quite a common corner radius on Imperial end mills because it leaves a much nicer finish, just like a round-nosed lathe tool does. Here's a cut that was made with that same end mill, and you can see that it leaves a perfect 1/32 inside corner radius on that cut. In addition to that corner radius, the other really important thing here is the width of this slot. There's a very tight tolerance on this because the axle box for the front slides up and down in this groove, so the clearances have to be just right for that motion to be smooth. I'm establishing my depth first, then I'm getting a rough idea where my width is. I know I'm still undersized, so I've got an adjustable parallel to see where I'm at now. And that gives me a starting point, but all of my checking and measuring from this point on is done with gauge blocks. So I cut and checked my way up to what I think is the final dimension. We need to be between 1.0 and 1.002 inches on this slot. Here's a gauge block stack of 1.001 inches right in the middle of that tolerance, and that is a perfect fit. Look at that. This gauge block stack, which is 1.0011 inches, 1/10 larger, does not go in. So we are dead nuts in the middle of that tolerance. Even a blind squirrel finds a tolerance sometimes. And of course the corner radius is correct because the end mill did that for us. Got a couple of other similar features to mill. I won't go into too much detail there. The final interesting feature is a kind of a house-shaped pentagon in the end. And this is clearance for the steam manifold, because of course the steam cylinders mount on the outsides of the frames, but the steam comes from inside the frames. So there's a manifold inside that sits under the boiler and distributes the steam to both sides into the cylinders, and that manifold is pentagonal and sits inside these clearance holes. For some reason I decided not to do layout for this. I'm just machining it to the DRO numbers, which I would have done anyway, but being a kind of house-shaped pentagon, it has some angled features that I actually can't easily machine in this setup. So after machining out the exact center lines with the appropriate inside radii, I realized I actually do need to lay out those angled features so that I can etch-a-sketch my way approximately up to those lines. I'm not going to try to machine those angled cuts. I'm going to finish those with a file. This is just a clearance opening for the manifold, so it doesn't have to be extremely accurate, but we want to be as accurate as we can, of course. While we're in this setup and we've got a common reference, it's a good time to drill a whole bunch of mounting holes for various things. So these are the cylinder mounting holes where the actual steam piston cylinder things that make it all go are going to mount. Then there's some holes around the axle boxes that are for mounting the cross members that join the frames together. Then once I'd gotten all my mileage out of that setup, I could take it down and then finish up the little houses over on the die filer, just filing to my layout lines. Certainly accurate enough for those angled features. Here we are so far, looking pretty good. The two axle box openings have little bridge pieces that go under the bottoms of them, so we're going to make those next. Now, of course, remember, we're making everything in pairs, so I've got some pieces of scrap, and I'm going to super glue them together so that we can machine the axle box caps as a pair, just like we did the frames. Once that super glue had cured, then I take the first pair of pieces and I square them up to dimension for these caps. This is for the front axle boxes. These have a couple of grooves milled right down the center of them. I want a really tight, snug fit on these caps, so I needle filed away the radius left by the end mill. There's no such thing as a zero nose radius cutter, so if you're trying to get a really tight fit on an inside 90-degree corner, then you got to do some filing, which I did. That's almost perfect. We got to do a little more filing there yet for a perfect fit. Then after that was done, there's one more relief that's down below those shoulders, and these need to be accurately dimensioned as well, so out came the gauge blocks once again. I didn't do as well as I did on the axle boxes. This time my 1-inch gauge block goes in there, but it's a little bit loose, so I think it's probably half a thou over 1. So we're a little bit below the middle of the tolerance, but we're in the tolerance, and I don't want to risk a second cut, so I'm going to leave that alone. I can always needle file it if I need to. Gotta say though, I'm extremely happy with that fit. That sits right down in there, no slop, no play, nothing. It's a beautiful fit. That is why I love this hobby. Then the second piece goes in the rear axle box. This is a little bit different. It's not a cap under the bottom, it's actually a T-shaped piece that goes into the axle box and fills up the space that we milled, because we're going to be milling out a bore into this whole area later. It's going to form a split bore, which then holds the bearings for the rear axle. This will all make sense later, but for now, just know that we need a very perfectly fitting T-block in there. I also drilled the mounting holes in all these pieces and then used those as drill guides to drill the matching holes in the frames. The holes were drilled with the tap drill size so that I can use it as a drill guide for the tap drill. Then I open up just the upper block area with the clearance drill, and then I can remove the block and tap the lower holes. These also, of course, need countersinking. Match drilling mounting holes for pieces that have to fit extremely accurately together like this works really well because it guarantees that the mounting bolts themselves won't mess up the alignment of the two pieces that you've just spent so much time making fit perfectly. Final test fit now of those cap pieces. Still got a really nice fit on there. That didn't change overnight. And those screws thread in there nice and flush. That all looks really, really good. This is all going so well because I'm really taking my time here. I'm trying to make everything as perfect as I can. The frames are just so important. If you make mistakes here, they're going to propagate through the entire locomotive, so everything's got to be as good as you can make it. Now finally I can machine down the ends, bring them down to final length. I had a challenge here though. I don't actually have a way to measure something this long accurately. I have rulers, but I don't have a caliper or something big enough to measure the length of these frames. Well, sometimes the universe smiles upon us. Right about the time I was thinking I need a way to measure this, a viewer reached out and said, "Hey, I have a 24-inch vernier caliper that I don't need anymore. Do you want it?" And I'm like, heck yes I do. And here it is, and it's beautiful. This thing is huge. It's the biggest piece of metrology I've ever seen. I think I could measure my entire first shop with this thing. But it was the perfect tool for this job. I did have to brush up a little bit on my vernier scale reading. Kids today are all spoiled by dials and digits on everything. Our parents went to the moon with slide rules, and I can't even manage to measure the length of a model locomotive frame without really thinking about it. Finally, as I mentioned at the top, there is an angled horn feature at the front of these frames, so I can do that now. I laid that out according to the drawing. Don't need more accuracy than this. This is just a decorative feature. I lined it up with the top of the vice jaw using an adjustable parallel, and I'll just mill down to that line. This is the final symmetrical feature on the two frames, so we no longer need the fixturing screws. I'm just going to mill my way right through them, starting with this one. It's a brass screw and some brass bar, so the mill didn't even notice it was there. Similarly, if you were paying attention, you might have noticed when I did the firebox clearance at the beginning, I had left the fixturing screw kind of sticking out in the open. This one edge was not yet finished, so we can do that now. Once again, milling right through the screw. I also took this opportunity to draw file that clearance a little bit just to fix the terrible finish created by that gap-toothed end mill. This isn't really important, but it was bugging me. You can also now separate those cap pieces that were super glued and machined together. A little bit of heat breaks that glue, and then some acetone cleans up the residue. You can also soft solder parts together for doing this kind of thing. That's a traditional way to do it, but honestly, super glue is a lot easier, works just as well, and is way easier to clean up than soft solder is. Alright, the big moment is here. We can remove the final fixturing screw and separate these frames. No turning back now. Look at that. That is two perfectly identical frames. We've got a couple of asymmetrical features to do. One of the frames has an opening for the mechanical lubricator, which is a locomotive-y way of saying oil pump. That has kind of a rounded rectangle hole in the frame that it sits in. There's also some mounting holes on either side of that are threaded for mounting that lubricator. The other frame has a couple of mounting holes for the main water pump. That's an axle-driven pump, and conveniently, or cleverly I should say, lines up with that final fixturing screw hole. These are clearance holes, so we just drill out the threads that were there, then drill the matching one, and we're done. No more fixturing screw residue. Oh, and did I mention that the cross-member mounting holes are supposed to be countersunk? Yeah, they are, so I went back and did that. There we are, two locomotive frames, one pair of frames as identical as we can possibly make them. There's a little bit more work to do. We have to bore out that rear axle box. And of course, there's cross members to make and front and rear bolsters and so on. But the frames proper are done. This is a big milestone on our little locomotive buddy. Here's a sense of how the frames sit in relation to the tender, give you a little bit of scale. The boiler, yeah, the boiler. Remember the boiler that we spent all that time making? It's been hiding in a drawer all this time. It's going to sit right about here. This big space up front is for the smoke box. Lots more stuff up there. But you kind of get the vague idea of how it all goes together now. Very exciting milestone to have those frames done. The locomotive is starting to take shape. Thank you very much for watching. Thanks so much to my patrons for making all of this content possible, as always. And I will see you next week.